let's take this term alone, the forward z traveling wave, e power minus alpha z. So you got e power minus alpha z v plus cosine omega t minus beta z plus phi plus. This is the real time domain signal, right? It's function of space and time. So what you see here is space. This is the V voltage, and in time, how does it evolve? Of course, it's a cosine function, so it has to be a cosine. But what happens to its amplitude? Is e power minus alpha z. So the amplitude is going to be decaying because this is like e power minus alpha z term. And when you multiply it by cosine, you know that the maximum value of cosine is plus or minus 1. So if alpha was 0, if alpha had been 0, then e power minus alpha z would have been 1. Then this guy would not have decayed. It would have been oscillating between plus 1 and minus 1. Nicely, it would have been oscillating between plus 1 and minus 1. But because of the losses, the three kinds of losses, resistive, dielectric, and radiative loss, which is a bad thing, you're losing the strength of the signal as it propagates through the medium, as it propagates through the transmission line. So if your transmission line does not have so much losses, then you will still receive something at this end. But if you are unlucky, then this guy decays so much that you are standing so far behind, then you will lose the information altogether. So losses are very bad. You shouldn't want to have any loss. So this transmission line having losses is one of the reasons why people started to look into wireless seriously, that you can transmit information at farther distances in a wireless mode, having lesser losses than you would encounter if you were to lay a cable from here to, let's say, Australia. If you were to send a signal from here to Australia, sending it over a wireless air medium is a lot more less lossy than if you were to lay down a physical cable between here and there. The physical cable would have so much loss that by the time it goes and reaches Australia, it's going to be dying off altogether. So that's how even satellite communication is possible, right? We are able to send signals from here to not just to our satellite, but even to down outer space, to even missions that are going beyond the solar system. So coming back to the ground reality here, the input voltage that you supply here is having a magnitude. The maximum that it can go is plus 1 and minus 1. That's the cosine term, right? It can go plus 1 and minus 1. And we say that it is V of 0 because since it's V of 0, that means Z equal to 0. So this means Z is 0. So if I go ahead and substitute Z equal to 0, this term goes off. This term becomes 1. So the magnitude that I can get for cosine is 1. How about the V out? If you notice the V out here, that magnitude turns out to be 0. Let's say for this example, 0.223. That means it has from 1, it has gone to 0.223. So what is the loss that you get? Yeah. So now we are going to have an important definition here. The loss is negative 10 log 10 of V out square over V in square. So in other words, this loss is negative 10 log 10 of P out over P in. 10 log 10 of P out over P in is your gain, isn't it? So this gain is going to be negative. This loss is going to be negative gain. So now V out is going to be 0.2231. So when you do that, you get up a positive loss. That means you're losing signal. Having a positive loss is not a good sign. Having positive gain is a good sign. Yeah, positive loss is not a good sign. Now let's say ideal world, when there are no losses in the transmission line, then your so-called R and G are going to be 0. What do we mean by that? If you go ahead and see this transmission line model, physically, what does it mean? I mean, R and G are 0. That means this guy and this guy are 0. There is no ohmic loss. There is no ohmic loss. These are the culprits that create the loss in the transmission line. When the resistance is 0, then there is no I square R loss. You know that an ideal inductor and an ideal capacitor does not dissipate any power. Does not dissipate any power. So ideal world, not a reality, is when the resistance and G is 0, Then if you go ahead and see your expression for alpha, the alpha will turn out to be 0. That means no signal is lost in the line. So whatever +1 that you have is going to go on. So there is a better way to describe this loss rather than just simply the ratio of V out over V in square that we did. Typically what people use is to define what is called as NEPA. NEPA is an alternate definition of loss, just for loss alone, yeah, just for loss alone in transmission lines is defined in terms of NEPA rather than in decibel. So how do you define one NEPA? That NEPA is going to be minus ln. Ln is logarithm to the base e. That is V out over V in. That is defined in terms of NEPA, just like how we define decibel. One NEPA is 8.686 decibel. So if you want to convert from NEPA to decibel, then you can use this expression, yeah. One NEPA is 8.686 dB. So previously we had 13.05, 13.04 as the dB loss. If you were to convert it to NEPA, then it's going to be 1.5 NEPAs. 1.5 NEPAs, for example, this 1.5 NEPAs can happen over a 30 centimeter cable. Over a 30 centimeter cable, then your alpha is this many NEPAs per 0.3 meters. 30 centimeter is 0.3 meters, which is 5 NEPAs per meter. So alpha is given in NEPAs per meter. So given a transmission line with the alpha value, you can always find out for 100 meters of the wire, what is the loss? For 10,000 meters of the wire, what is the loss? You can go ahead and figure out in NEPAs or in dB by using this conversion here.